Welcome everybody to this virtual Europar keynote session to be delivered by Ewa Deelman. Ewa Deelman is a research professor of computer science at the University of Southern California with Information Sciences Institute. She's been internationally known for the pioneering work on scientific workflows, for which she received many awards. She's an IEEE fellow, she's a Europar friend. Even though she spent most of her life in the United States, she's also one of the top Polish computer scientists, as she was born in Warsaw. So it's a very great pleasure to welcome her for a keynote talk, the first time that Europar is organized in Poland, technically at least. So Ewa, thank you very much. Over to you.
Riza, thank you so much for this kind introduction, and to the organizers for inviting me to give a keynote at Europar. I'm really sorry that the conference could not be done in person because, as Riza says, this is my hometown and I would love to see Warsaw. However, I have to say that there are some benefits to having this event virtual. So through the great organization that Maciej Marlawski and Krzysztof Rządza have done, I feel like I already met a number of you on Slack, and I love the introductions channel where people talk about themselves and what they do and what papers they present. So keep it coming. This was really nice. So in my talk, I would like to explore how automation is changing the way we do science and the challenges and opportunities that we see in that context. Right now, we see automation in our everyday lives. And it's also an important part of the science life cycle, where we use it mostly to automate the computations on a variety of computing resources, do data analysis and other tasks. If we look more broadly at the scientific research process and discovery process, we can define it in the stages that you see on your screen. So you might start off with asking yourself a question. For example, one that I keep asking myself is, when will the COVID vaccine be available? Then you might want to do some research, look at papers that have dealt with this issue in terms of similar types of vaccines being developed for other types of purposes. You might form a hypothesis that the vaccine will be available in 6 months. Then you gather your resources, so how you're going to conduct your experiment. So you might figure out which data sources you're going to use, which simulations maybe you're going to perform. And then you actually perform the experiments, you collect the data, and then you go into the stage of analyzing your results via different types of methods, computational methods most likely. And then finally, you interpret the data to see if it actually supports your hypothesis or not. If it does, or if it does not, sometimes you also might want to publish negative results. You publish the results. During the time, you can also, at any point in the cycle, you might go back to revisit, do some further research, adjust your hypothesis, or gather additional resources, or conduct experiments. Traditionally, if we look at where automation really has helped us in the cycle, it's really in the 3 stages of gathering the resources, so identifying the different sources of data that you want, performing the experiment and data collection, and then the analysis. So in the next slide, I'm going to unroll this a little bit of the cycle and look at these 3 bottom parts of it. So when we talk about this process, we can look at it as gathering data, discovering what types of archives are available, what data is available to do your research. You identify the computational resources that you need to do the computing. You find the codes, maybe there's a community codes, Python notebooks that you can use. You might also want to write additional codes to support the experimentation. And then oftentimes you put this all together into a workflow where you define the tasks that you want to execute, the data that would flow into these tasks, and then having this kind of high-level description of what you want to do, so the science aspects of this computation. you might want to execute it on different types of resources based on the needs of your workflow. So it could be your campus cluster, it could be a high performance computing system, a cloud, and so forth. During the execution, you want to monitor what's happening with your computations, and if there are any problems during the execution, you might want to discover the failures and recover from them. Obviously, you also want to collect provenance information, so information about how the results are being obtained. Then finally, you get results and you can do the result interpretation. So traditionally, when we looked at what part of the cycle we've been automating, we've really been automating the cycle of the workflow creation through the result, obtaining the results. So I'm going to look at the opportunities and challenges that we have in these areas. However, first I'll talk about why people want to, in general, want to use scientific workflows to structure their problems. So oftentimes workflows are easy to use. So once you structure the problem, you can reuse them as well. And they are often portable across platforms and scalable. So if you describe your workflow in an abstract enough way, others can pick it up and run it on different infrastructures. With different types of data, you can scale up the workflows to greater sizes. It also can be shared with others. So once the workflow is designed by a specialist, by an expert in a particular area or a team of experts, you can share it with others, with students and postdocs and other colleagues. And once you have a workflow, the workflow management system can automate the execution and performance optimization. It can help recover you from failures. It can monitor the execution. It can also help you debug the problem, pinpoint where the issues are, and it will collect the provenance information for you. And throughout this process, we have used various heuristics to optimize the execution of a workflow and to detect anomalies. And I'll talk a little bit about that down the line. However, first, I wanted to give you some examples of what types of workflow applications we're talking about and what applications people are using. I know many of you are familiar with the Montage astronomy project. This is a project led out of Caltech by Bruce Berriman. And the goal of this project is to provide a service to the community. So the user comes into the Montage service and they ask for a particular area of the sky. And the service generates a science-grade mosaic of that area with a particular size desired by the user. So in this case, the data, they want to make the data and the derived data available to a broad range of users. However, oftentimes they may have small computational requests that can be handled by the local resources. However, if they get a larger request, they might want to use the national cyber infrastructure or cloud resources to do the computing. So for them, the benefits of using the workflows is they get the automated on-the-fly workflow generation, and also the ability to port the workflows to different resources and automate the data management, the data transfer across the various systems. Another type of application that we've been working with comes from the Southern California Earthquake Center. This is the CyberShake application, which asks a question: what will the peak earthquake motions be over the next 50 years in a particular geographic area? In the middle bottom, you see a visualization of this type of information on the map of Southern California, and the little points on the map represents the different workflows that I run to calculate this map. This type of information is useful for building engineers to design codes for buildings that can withstand earthquakes, disasters planners that look at what to do in case of disasters, how to stage the supplies, and insurance agencies when they insure property. So in the case of the CyberShake applications, the codes are very complex physics-based simulations that run on high-performance computing infrastructures, followed by some post-processing. These codes are collaborative design that are strung together to model these very complex systems. And for the SCEC, the important part is to be able to correctly connect these components, but also automate the flow of data from the simulations, for example, to the post-processing. A long time ago, this was really done via emails. Obviously, that automation can quickly solve this problem. And the other part is that they wanted to, because the simulations were so complex and involved so many components, they wanted to have automated failure recovery and supports for scalability. So if in the red rectangle that you see on your screen, this shows you the map that was generated for Northern California, now I think a couple of years ago, that was run on 2 high-performance computing systems in the US. The computations took 120 million core hours. They were composed of almost of over 39,000 jobs in the various workflows. The amount of data that flowed through the workflows were about 1.2 petabytes, and then the output data was over 14 terabytes and that was archived. So even if you're working alone, or maybe even particularly when you are working alone, the workflows can give you the power of many. So for example, in her PhD work at University of Arizona, Aria Glasstein has used workflows and to automate, to answer the question that she posed. So her research question was, how did humans spread across the world? And the secondary question was also, what demographic events led us to where we are today and the diversity we see? To answer the question, she gathered her resources. She used a large number of SNP and whole genome sequence data to do her analysis, and the power of the open science grid and its high throughput computing resources to get the answers. In this case, she needed to perform a large amount of analysis on large scale data sets, and she needed to also automatically adapt to the dynamic resources of the open science grid, where the resources are available based on the usage, shared usage by others. She also needed to obviously record how the data was produced and also automatically scale the execution and provide good performance. In her case, she executed her workflows over 40 different execution sites of the open science grid. And you see the graph on the bottom left that shows you the number of war hours that were done at the different facilities. Over time, and the colors represent different facilities. She ran approximately 12 million jobs and that were in 342 workflows and consumed about over 7 million of core hours for her computing. So we can focus a little bit more into the workflow lifecycle itself and see what are the various steps from the composing of workflow template at the top, where you identify the various components, the various computations you're going to perform. You then might populate this template with data. So you query metadata catalogs to find the data that's needed for your research. In some cases, you might start with the data and then populate it and then generate the template. So figure out which components you need to answer the questions. In any case, you end up with a workflow instance, which describes at the scientific level what computations need to be done. Then this is oftentimes a resource independent description. So you want to map this description onto the available resources that the user has at hand, which gets you an executable workflow. Then you execute this workflow using a workflow engine on various compute storage and other network resources that are distributed oftentimes in the environment. These will generate the data, metadata, and provenance information about the execution. And finally, you may also want to store this in a database, so it can be or data repository, so it can be found in the next cycle by others. If we look at the various parts of the cycle, so we can divide it looking at the workflow creation, workflow planning, schedule and execution, and reuse. And I'll talk a little bit about the automation that can be done or has been done in these various components. And components of the life cycle. So I actually back and also looking a little bit towards where the current AI technologies, so where AI can help us with some of this automation. So back in 2001, 2002, when we started working with LIGO, which is the Laser Interferometric Gravitational Wave Observatory, we designed an interface in which the LIGO scientists could describe a high-level workflow at a very high level, basically defining the metadata for the particular request. So this was for a pulsar search, looking at emission of gravitational waves for a particular time period. And then from this request, we used the AI planning techniques to generate a workflow, which then was executed on behalf of a user. And in the end, working with LIGO, the scientists didn't really want to have the interface that you see on the left. They really wanted to manipulate the workflow itself. So at that time, the system for them seemed to be too rigid and also lacked transparency. So they didn't see how things went from this high-level description to the actual workflow, and they wanted to manipulate the workflow. So one open question here is whether current AI techniques can improve this process, maybe not for LIGO, but maybe where scientists really want to get down to the nitty-gritty of what's going on, but really to broaden the appeal of scientific workflows and raise the abstraction to this higher level. In terms of the second part of a life cycle, which we called workflow planning, which might be a little bit confusing with the previous step, which was workflow creation. In this case, we plan this the workflow instance onto the available resources. Oftentimes, as I mentioned, these resources are distributed in the environment, so you need to know the details of these resources and tailor the execution to them. Oftentimes workflow tasks can be small, so you need to increase the computational granularity of each task to make the execution efficient. The workflows themselves can be large, and so it's hard to manage these large chunks at a time and do the mapping, so you might want to reduce the number of tasks. And there or restructure the workflow, and there are system and network overheads in executing these workflow tasks remotely. So sometimes you might want to provision resources ahead of time or send more work at a time to these resources. Also, sometimes we move the data to the computation, so we stage it automatically after we discover where it is. If sometimes it can be also replicated in the environment. And sometimes computations need to be moved to the data for issues of performance, of privacy. So you need to be able to make these smart decisions and explore the benefits and drawbacks. In our Pegasus workflow management system, we've done a number of different optimizations based on heuristics. So we do task clustering to increase the granularity, computational granularity of the jobs. We also collocate tasks on resources to get better resource utilization. We do structure workflows in a hierarchical fashion. So you have a workflow within a workflow, which allows the system to focus only on the smaller portions of a workflow at a time when doing the planning. And we also have data reuse, where we see whether the data was previously already generated, maybe through a different workflow execution, and we can reuse it, so execute only a portion of a workflow. In terms of a workflow execution, there are other challenges that we face. Oftentimes computations fail. Sometimes the codes are buggy, so you can automatically checkpoint the workflow and restart it. You can pick up also a different code, or you can sometimes the code when restarted, tried again will succeed. Sometimes the resources where you're executing fail. You can again retry, maybe you get a different node or you try a different resource. The services such as data movement, data registration can fail. So there's retry mechanisms you can do, or you can choose a different service. Sometimes you also run out of resources, or resources get filled up. So you can, and you see that on the right, you can analyze the workflow and add these data cleanup tasks in orange to clean up the data from the execution side as the workflow progresses. So it's we see now the growth of AI, a use of AI, and the growth of AI for automation. We have started exploring its applicability to some of these aspects, so anomaly detection, failure recovery. So I'll talk a little bit about that in a few moments. However, before I do that, I wanted to touch about the automation at the higher levels, the upper levels of a workflow lifecycle. I already mentioned the workflow creation, so use of AI planning techniques that might be a possibility down the line to be used to improve this process. And another part of a workflow lifecycle that's been often problematic in terms of automation was the reuse of workflows, because it's hard to interpret and modify the workflow by others, but also it's hard to execute these workflows on different platforms. And so recently, the Chameleon Cloud Testbed has made it easier to execute not only and reuse not only workflows but codes in general. So they combined, and this is a project led by Kehit Argon. They combine Jupyter Notebook's ability to represent the experimental process with a complex environment in which the experiments occur. So on Chameleon, you can provision multiple nodes with multiple switches. You can connect them with multiple networks and all develop this very complex experimental environment. Through this integration, you now can talk about this complex environment as one and embed it in your Jupyter Notebook. You can also name these containers, and also you can export the whole thing to Zenodo and have it citable. So you get the DOI, and you can share that DOI with others, so they can retrieve your entire, somebody else can retrieve your entire experimental setup. Another thing that you can do is actually automate the resource provisioning process. So if you think about this, there are various pieces that you need to have in order to be able to do that. When we call this the ultimate workflow management system. So this is something that we've been researching within the Panorama project. Here, when the workflow is submitted to this ultimate workflow management system, we rely on performance models to request a certain amount of resources needed for the execution of a workflow. There might be also some negotiation at that phase, and then depending on the resources that we get, we can also use the performance models and sometimes simulation to predict the workflow behavior on these resources. And if we look at, again, where we can improve the process with AI technologies, for example, we can use AI to help develop these potentially better performance models. Once you have the resource provisioned, you can go into the workflow execution and workflow and infrastructure monitoring. And from there, you can also add other components to the system. So you can add in anomaly detection based on the infrastructure that you're monitoring, and also potentially on the performance models that you've developed. However, all of this makes the system very complex. So that's why this is still in the research phases and not available in the Pegasus development releases. And the other part, however, what is available in the releases is the improved infrastructure for monitoring and collecting monitoring information. So in order to do anomaly detection, and especially if you're looking at AI techniques, you need to collect a large amount of data. So you need to be able to collect the data from both the infrastructure and the execution of the workflows. And we have integrated this with sending the data to message queues, which then distribute the data for visualization, for anomaly detection, and other components of a system. So I think with AI and machine learning techniques coming online, we see a number of opportunities to make the workflow management systems more autonomous. There are two areas that we're working on currently, anomaly detection and anomaly error classification, but there are others that I think would be applicable as well. So looking at predictive models of performance, workflow reuse recommendations, so maybe based on the types of data that you have, it can recommend the workflows that would be suitable for that, and many others that we can think of. However, there are a number of challenges when you apply AI techniques for automation. You need to be able to collect enough data, and it has to be quality data, it has to be rich enough, it has to be balanced across various class representations. In some cases, you need to have enough labeled data, or you need to also apply techniques to do data augmentation if you don't have enough data labeled, so do pseudo labeling, for example. You also need to be able to restructure the data to be amenable to the application of current techniques. So you can, maybe you have to normalize, scale, transform it in some way, or you can also work on development, obviously, of novel AI techniques, but that requires very specialized knowledge as well. Also, when you're applying AI techniques, it's not, for example, or deep learning architectures, you need to worry about things such as hyperparameter optimization, so setting appropriate learning rates, number of epochs, hidden layers, and activation functions, and others to actually make the models train well and then predict well. So one of the areas that we looked at, so Anirban Mandal from Renzi led this effort of looking at k-means clustering to do anomaly detection on the execution of workflows in various environments under various conditions. So in this case, he executed the workflows under normal conditions and also with various types of fault injections. He defined a feature vector for data collected for each workflow, and you see them in the table right here. So some of them that are actually graphed on the right have a number of jobs succeeded to the ratio of jobs being done. Also looking at the duration of successful jobs versus the number of jobs that succeeded, and also the duration of failed jobs versus the number of jobs failed. And you can see on the right, these are normalized scales, which show you that the clean workflows cluster together at the bottom right in green. And then you have various types of fault injections that are shown in different colors that also cluster together in a different area of a graph. So you can use these techniques during the execution of a workflow, monitor these feature vectors and decide what is a very large workflow is doomed for failure, or will it succeed? We also see in people using deep learning techniques, and in particular in image analysis and classification, to approach different problems. So my students Patricia Kravchuk and George Papadimitriou ask the research questions: can you use these deep learning techniques to detect and characterize different anomalies that you see during workflow execution? So here you see the normalized Gantt charts of the execution of a workflows. At the bottom, you see the different parts of what different colors mean. So the red, you have the delay in starting the jobs that are ready to execute. So this is often caused by the limited resources. You see the workflow management system delay, which is basically the time for the workflow management system to react to the changing availability. Queue delays versus waiting in queues at the remote resources, and in blue you have a runtime. The three different Gantt charts show the normal execution and the different anomalies being introduced. The one is hard drive load, and the other external load, and one is network packet loss. And by the naked eye, you cannot really tell many differences. And so we are attempting to use deep learning techniques to do the analysis. We formulated the problem as a workflow where we collect the data, we convert the logs that are unit timestamps into delays. We then prepare them, the information for plotting. We plot this information, and then we apply, we divide the data into the different training, validation, and testing sets. We use Automat to do hyperparameter tuning on our ResNet model. And then we validate, look at the training validation set, and we also, we look at the results of these classifications. And unfortunately, right now, it looks like we're not getting very good results with our testing set. The errors, predictive errors, are still high, and we think it's probably because we don't have enough data, but stay tuned, we will have more. We also see this approach of using workflows in other machine learning applications. This is the automated detection of COVID-19 and X-rays that was published in the paper that you see on the bottom. So the scientists here use the different stages of a workflow to figure out what types of architectures, deep learning architectures, will give them good classifications of chest X-rays as being COVID positive or COVID negative. And also the scientists give these models to others so they can explore on their own. So these are pretty complex workflows. The machine learning part is actually just a small part of these workflows. If you look at another workflow from literature, this is the land cover classification. It also shows you the various stages, and unfortunately, I don't have time to go into many details. The systems under various cases. You also want to improve then the segmentation quality. So in this case, we put deep learning models with selective search methods, and finally you end up with models that are suitable for different types of data. However, all this is at a cost. So this is a graph from a recent paper on energy and policy considerations for deep learning in LP. And the graph shows you the amount of CO2e consumed by these different types of activities. At the bottom, it's a travel of one passenger from New York to San Francisco, which consumes 1984 of these pounds of CO2. However, if you look at average American life, we're looking at over 36,000 of these units. If you do a natural language processing pipeline with tuning and experimentation, so something you might want to publish in a paper, you're actually using twice as much, so 78 over 78,000 pounds of CO2. And this is, if you compare it to a car with average fuel usage for a lifetime of a car, it's about 126,000 units. So you see the difference. And then if you do an NLP transformer model with tuning, experimentation, with searching the best parameters for the models, you're looking at incredible amounts of CO2 that's consumed over 6,026 units. So obviously, what you need to do is, the community needs to do, is to improve the efficiency of these computations. But I think as a system people, we can also help as well, and really look at managing the resources better and manage with looking at different types of constraints. So in addition to resource capabilities and the traditional things that we looked at the time and budget, we can also look at things such as use of renewable energy. So from the literature, from the same paper that I quoted before, it looks like Google Cloud is actually using a lot more renewable energy than others. So maybe this is a choice you want to make when you're concerned about these items. Also, if we look at the execution environment, it's very complex, and which makes the problem hard. So you have various resources that you can use. So high performance computing, distributed computing, clouds. You also have edge devices where some of the computations can take place. The high performance computing systems are becoming much more complex and heterogeneous with various data storage, burst buffers and others. They're also increasingly faulty. So they look kind of more like the distributed systems. So maybe some techniques are applicable there. The distributed systems are also becoming more complex. You can have software-defined capabilities, especially within networks, which can now be also programmable. You have very special data storage that comes into play here as well. And then clouds are becoming a new platform for science, but they can be very heterogeneous and costly. And again, have these energy considerations as well. So we need to be able to collect a lot of information to make these smart decisions, both at the application and the resource level. We also need to deal with this distributed environment that's faulty. So fault detection and attribution, I think, are going to be becoming much more important. And then we're using automated techniques to adapt maybe the workload, but also the resource management approaches that you have to these various settings. So if we're talking about using more AI in our work and making the decisions, in addition to making the systems more complex, what we provide to the users, the complexity of that grows, and the resource cost grows as well, as we've seen. There are also issues of trust. So how do we know that what we observe is real? We have issues of transparency and explainability. So can we actually see how things were happening? Can we explain what happened? Can we understand how the particular results were obtained? Do we know what data sets went into the training of the models, for example? And also issues of reproducibility. So we talked a lot about workflows helping you with reproducibilities. AI and the automation that we put in will actually make it potentially much harder. So if we revisit this life cycle, which I started with at the beginning, and we ask ourselves, can AI take over scientific research and where it can help? So traditionally, we thought really at the bottom of our life cycle where we already do a lot of automation, that maybe AI can help there. But also it can help in other places. So there was a journal article, an initiative of Science magazines a couple of years back devoted to the topic. And they're quoting a number of things such as Semantic Scholar that can help you with your research, find the appropriate citations. They talked about Zimmergen, a company that can track various variables by treating microgenome that can help you form hypotheses. They talked about wet lab experimentation on the cloud. They talked about Newtonian, which is a software platform that ingests large data sets and spits out mathematical models. And then Cytomatic, which helps you find citations while you write the paper. But 2 years, went by, and there are other things that can help you today. So COVID Scholar is used extensively to find relevant articles for when you're doing COVID-19 research. AlphaFold can predict properties of protein from genetic sequences. And then you have GT3 with OpenAI, which can not only find your citations like Cytomatic, but it actually can write the paper for you. So in conclusion, we need more automation in science. We don't know yet how to automate our work, and we have to find ways to keep up with the pace of change. So this is the text that I actually got. I was reading an article about teaching GPT to transformer, a sense of humor. I took some of examples from there without teaching the sense of humor, just using the Python code and fed it to GPT-2 medium. And I gave it a sentence in conclusion: we need more automation in science. And it wrote this nice paragraph for me. It didn't quite finish it, so that was upsetting. But it did tell me that the work of a global science and innovation initiative, which apparently I'm leading, is an example of this. The GSI is a project of the European Commission, funded by its science, technology, space, and innovation budget. It has a website, and I'm thanking the European Research Council for the support of this work. So this was kind of freaky, given that I was giving a talk at Europa in Europe, and I live in the US. So maybe there's some more information that was leaked into this engine. In any case, so we see that automation is already changing the science and the work. It will also change the workforce landscape. So the question that I want to pose is to you is, will we still need scientists? What will be the role of the scientists in the future? How do we reinvent ourselves in the era of automation? How will it be different? How do we also interact with these new capabilities? So whatever expectations, whatever levels of trust. And I just want to leave you with this final quote from an article in Quantum magazine. And this is quoting Kai Lars Polster from Heidelberg. And he said that to be creative, you have to dislike being bored. And I don't think a computer will ever feel bored. So I hope that we feel bored more often. And I think these days we are, so we'll be potentially more creative. Thank you.
Thank you very much, Ewa. That was really very, very interesting. Lots of information. I think it's now time for questions. I believe people can write questions on Slack, even though nobody has written something. Ewa, can you read on Slack the question?
Let me see.
I mean, Maciek is asking, are currently available AI techniques sufficient for workflow management systems, or is there a need to develop new methods?
So I think we need to have some adaptation, at least, to the methods that we have today, and make them more transparent and explainable, so that we know when we apply these methods in scientific context and in automation in particular, that we know what they're doing. So even with the methods that we have today, I think there's more work. But also, I think that the methods need to be developed that combine information from simulations of the heuristics that we developed in the past with the AI techniques, so we have more a more controlled environment in which we work.
Okay. Other questions? I have a question, but and let me ask, since there is nobody else. I believe there is a difference between AI techniques. You mentioned this early work that you did on AI mapping in 2001, 2002. And I believe this is really different from what we're talking, which is machine learning techniques. So for example, you can explain what is happening with AI mapping techniques. But I don't think it's acceptable when you cannot explain things. So I don't know if you can draw the difference between the two. I mean, machine learning to me is a bit of a mystery, and sometimes may give you results that you cannot explain anyway. And so the question is, do you really accept something that you cannot explain?
And I think that's where the scientists come in, right? Because we don't accept that. Even the example that I had with giving GPT-2, one sentence, it's an okay text, but it's not mine, and I cannot explain how it derived that. I give it the same sentence a few times and got different versions, and maybe for the creative process, that might be interesting to see what happens, but it's not good for science. And especially when people are talking about using AI to control instruments. This is obviously a very important part of automation, and making the scientific instruments work better and more efficiently is great, but you need to worry about whether they would act correctly under various circumstances. So have the behavior reproducible at critical times, and also can you understand what they would do?
Okay, thank you. Somebody else, another question. Maciek, do we have now a reception?
I have so there is a question from Ivan Carrera. Do you think we could automate explainable AI in the same way? So I'm not quite sure the context, fully understand the context in the same way as what, but I think, there will be more automation, and we just need to guide it. And a lot of AI work obviously has been done in the industrial arena. So industry has been championing, Google's and others have been championing the use of AI for their work for natural language processing, machine translation, recommendations for what to buy and so forth. And I think it would be good for us to engage more with industry and to work together on this more explainable and predictable AI in some sense, so that our voices are heard. And I also know that the industry is also looking very much into scientific applications as well. So Facebook and others are using AI for science. But I think we can, as scientists, we can play a bigger, and computer scientists in particular, we can play a bigger role in shaping the future. All right, I don't see any more questions on Slack, but again, it's very nice to see everybody on Slack, and I hope that Maciek and Krzysztof keep the Slack going. Maybe it will be picked up then for next year. But I think it's a really nice place to see old friends and to meet new people. And if folks are interested in someday coming to LA doing postdoc or being graduate students in my group, you know how to reach me.
Great. So thank you very much. I don't know how we can upload.
Yeah, I can upload myself. Thank you for attending.